So welcome back, dear students. I'll be explaining you the same topic of fluid statics, in which I'll be taking you to some of the difficult level problems on the topic of Archimedes principle and buoyancy forces. So in this video, I'll be telling you 5 problems and further 5 problems in the next video to make the video less linear. And to grab your attention, after each problem, I'll be giving you a question similar to a similar question I will be posting you so that you can practice in your notebook. So you can pause the video in between and see the answer after you have solved it, or you can note down the questions and solve it after you watch the complete video. So let us see the first question. So this is problem number 1. So what it says is that in air, a metallic sphere with an internal cavity weighs 40 grams. So there is a metallic sphere which has a cavity inside. It's an emptiness inside. If you weigh this in air, so attached to a spring balance, it weighs as 40 grams. And the same in water. So weight in water is given as the 20 grams. Okay, why the reduction in the weight? It's because of the buoyancy force. So the force of buoyancy, or we can say it is the net reduction in weight or apparent loss in weight, is weight in the air minus weight in the water. So which is 40 minus 20 is 20 grams. But what is asking, the volume of cavity is how much? So we know the formula of force of buoyancy is nothing but density of the liquid into volume of the solid into g, which is turning out to be 20 g, and from which we can get g get cancelled, take g as the acceleration due to gravity, and we can get here volume of the solid. Volume of the solid is force of buoyancy, which is about 20 here, 20 upon density of the liquid. So which is 20 upon density of the liquid is 1. So volume of the solid is 20 centimeter cube. Now this volume of the solid is the complete solid. Okay, complete solid along with cavity. Now when it is weight in air, the weight in the air is nothing but mass times gravity, and this mass can be written as density into volume into g again, but this density is the density of material, and whereas this volume is volume of material only, subtracting the cavity, means cavity's weight is not it is not measured by, because it is empty, it is only measuring the material, not the cavity. And the density of the material is given as 8. So we can write here 8 times volume of the material into g equals the weight, which is 40g. So gg cancels, volume of the material is nothing but 40 upon 8, which is 5 centimeter cube. So what is the volume of cavity? Volume of the cavity will be volume of the cavity plus volume of the material is nothing but volume of the entire sphere. So from where volume of the cavity is volume of the sphere minus volume of the material, which is 20 minus 15, so 20 minus 5, which is 15 cc. So the answer is 15 centimeter cube. The volume of cavity is 15 centimeter cube. All right. So now I'll be giving you a similar problem for you to practice. So here comes the similar question in which what is given in air, a solid weighs this much, and when it is immersed in oil, it weighs this much. The density of the oil is given, and what is asked here, the density of the material of the object. So it is similar to the previous problem. Give a try, and you can pause and give a try. Okay, if you finish doing, the answer will be 2.4 gram per cc. So all right, let us see the question number 2. What it says is that, so a vessel filled with water is kept on a weighing pan. This is the vessel shown here. It is filled with water and kept in a weighing pan, and it's adjusted to 0. Now it is 0. We can adjust it, right? So a block of mass 10 kg, this block you can see is 10 kg, is suspended by a massless spring of spring constant K value is given, spring constant. This block is submerged into the water in a vessel such that the elongation in spring is 10 centimeters. How much it is submerged? It is equal, it is submerged in up to a point where elongation in the spring is 10 centimeter. The reading of the scale is how much? Means this is scale reading will be how much? So if you see the forces acting on the block has got the weight of the block downwards. The tension is upwards in the string, because obviously this tension is the spring force because it's a spring. And there is one more force which is acting on the block due to the liquid, which is by the immersed part of the liquid, is nothing but the force of buoyancy. Right. So if you balance we can see that tension plus force of buoyancy is equal to the weight. So let us calculate the tension. The tension is nothing but the force of spring, which is nothing but K times X. K is given as 100 Newton per meter into X value is 10 centimeters. So I can get 10 by 100 meters. So 100 cancel. Our spring force is turning out to be 10 Newton. Meter cancel. So let us now calculate the weight of the block. Okay, already the weight is nothing but the mass is given as 10 kg. So weight is nothing but mass into gravity. So which is 100 newtons, right? The weight of the block is 100 newtons. What is the now force of buoyancy acting? So this is weight minus tension, which is 100 newtons minus 10 Newton is turning out to be 90 newtons. This force of buoyancy is nothing but the scale reading that we have. So the scale reading will be 90 newtons. So we have a similar problem in the next, I will be showing you the similar problem. So we have a similar problem here where what it says is a beaker of water rests on a scale with reads 50 newtons. 50 Newton is a beaker weight plus water weight. So a metal block of mass 3 kg and density given are fully submerged into the water while suspended by a string, not a spring but a string from the rigid support, as similar to the previous one. Previous one it was having spring, now it is just a string. So you have tension, you don't have to bother about the spring constant. So what is the new reading? When we suspended it, what is the new reading? Okay, pause and try on your own, and after you try, the answer will be 60 newtons. So all right, in this question, what do we have is a cubical block of wood of cube of the edge is 3 centimeter floats in a water. So it's a cubical block, it's basically floats in the water. So the density of this block is 800 and the water density is 1000. So first we need to find out how much of the volume of this block is inside and outside. So we have the formula of volume inside by total volume is nothing but density of the solid block by density of the liquid. This is from laws of flotation. So we can get here the volume inside, which is equal to density of the solid is 800, the wooden block, by 1000 into total volume, which means here 0.8 V is the volume which is inside the liquid. It's already inside. Now what is the volume outside then? It is 0.2 V. 0.2 V is the available volume outside. It means until this volume gets submerged, you can keep the weight. You can keep the weight inside that until that volume is submerged. Means some extra buoyancy force of 0.2 V supporting the 0.2 V or submerging the 0.2 V is available. Apart from that, it is connected to a spring. So when I press it, spring also this weight will press it this little bit, so spring also get compressed, right? So now the spring force is turning out to be Kx. So K value is given as 50 and X values are the length of this length of the cube, so which is 3 into 10 power of minus 2. So which is 15 into 10 power of here again minus 1, so which is 1.5 Newton. Okay, so now we need to calculate the force of buoyancy, that extra force of buoyancy that can support, okay, when we keep the maximum force. So that is nothing but the density of the liquid into volume of the solid into G. Okay, so density of the liquid is 1000 into volume of the solid, or what volume of the submerged part. Okay, so yeah, we are not going to give you a submerged part this because this is already submerged. how much extra is available for submerge is 0.2 V. So 0.2 V times the G value we can take as 10. So now we can substitute the values. It is 10 power 3 into, you have 0.2 into volume. If you check out, the dimension is 3 centimeters. So volume is turning out to be 27 into 10 power of minus 6 meter cube into 10. So we do have here 3 and here your 1 4. So here it is minus I think 3 plus 1 4 minus 2. So yeah, so what is that? That's it. So now from here 27 twice is 54. So 54 into 10 to the power of here minus 3. So it is 0.054 newtons. This is the force of buoyancy supporting that. These two forces are acting basically upwards, the force of buoyancy and the force of spring. To this, if I add an additional weight on this, so the weight of the block and weight of the additional mass is acting downwards. So this, when balanced by these two, it means this entire wood is inside the water without the upper mass getting wet. So let us find weight of the block. Weight of the block is mass times gravity. Mass of the block is density into volume into G. So density of the block is 800 into volume of the block is again 27 into 10 to the power of minus 6 meter cube into G is 10. So we have here 2 zeros and 3 and here minus 3. So you will be getting here 216 into 10 to the power of minus 3, which is turning out to be 0.216 Newton. So this is the weight of the block. Now what is the weight, additional weight, that maximum that can be added is from here balance. So weight of the the spring force plus the weight of the buoyancy force minus weight of the block. So the spring force, we got it to be 1.5 plus the force of buoyancy we are getting at 0.054 minus the 0.216, which is turning out to be 1.35 newtons. So this is the answer. So here we got a similar question wherein a wooden cube, the dimensions are 4 centimeter and the density of the wood is now different 750, and K value, the spring constant inside is 40 Newton per meter and the G value 10. So the similar problem, very same, the values are changed. You can do, pause the video and you can do, and if you finish it, you must be getting the additional weight, the maximum additional weight will be 1.712 newtons. So all right, in this question what we have is a fluid container is filled is containing a liquid of density rho, is accelerating upward as shown in the figure here with an acceleration of a along the inclined plane of an inclination alpha. Okay, this is the vessel containing the liquid, and when this is accelerating, then definitely the liquid will take this shape, okay, by making angle theta from the free surface. What is the theta, he's asked. Okay, so let us take this liquid, the same liquid, when it is accelerating on a plane surface. Okay, let us say that this is accelerating on a plane surface with an acceleration a. Definitely the liquid will be like this, it is making an angle theta with the surface. Okay, and now for this liquid the gravity is acting downwards. Okay, we have a small derivation for this, that the tan of the theta will be equal to the horizontal acceleration by vertical acceleration. So applying the same strategy over here, but for the inclined plane we need to find out the horizontal acceleration. We can say the acceleration horizontal by acceleration vertical. Okay, vertical component here, horizontal component. The same thing we apply over here. So if you see, we take the components of the along the inclined plane. Okay, so if this is alpha, the mass of the liquid is experiencing a force which is here G. So this side is one force, this side the another force, this is alpha and this is alpha here, so which is G cos alpha, and this side you have G sin alpha. And because it is accelerating, this fluid is experiencing a pseudo force or pseudo acceleration in this direction, so which is A here. So if you see, the net horizontal acceleration is this two, so A plus G sine alpha. The net vertical acceleration is G cos alpha. So as we apply the same thing, the tan theta, the angle over here is nothing but the horizontal acceleration by the vertical acceleration. The horizontal acceleration is A plus G sine alpha upon the vertical acceleration is G cos alpha. So the angle theta is given by tan inverse of this A plus G sine alpha upon G cos alpha, sorry. So that is the theta, which is the option B. So now the time for you to practice a similar question. So we have a very similar thing here, arrangement, a trolley and a container filled with liquid that accelerates downwards. Now this is accelerating downwards, okay. The previous question was it is accelerating upward, now it is accelerating downward. Everything is same, you need to find out the theta over here, okay. So you can pause the video and try. So okay, so if you finish trying, you will be getting the answer as tan inverse of G sine alpha minus A upon G cos alpha. Okay, that's it. Okay, in this question, a tank accelerates upwards with an acceleration of 1 meter per second square. It contains the water and a block of mass 1 kg, and the density of the whose density is this is held inside the tank with the help of a string as shown in the figure. Now the tension in the string is how much? He's asking the tension in the string. So water density is given, and the density of the block in SI unit will be 800. Okay, so 1 kg, this is the SI unit, this is the SI unit. So let us move on to the problem. If you check the forces acting on the block, okay, the force of buoyancy is acting upward. This time the force of buoyancy is rho v effective G, because the vessel itself is accelerating upwards. So what is the effective G? It is, when it is accelerating up, it is A plus G. Okay, we have to use A plus G here. And downward it is the weight. Weight is again mass into G effective. All right, so which is mass into G plus A, and here rho v G plus A. Okay, so now we need to calculate this too. Okay, what will be the tension in the string? The tension is the resultant of these two. The tension in the string is the force of buoyancy minus the force of, okay, the weight. So let us find out force of buoyancy first. The force of buoyancy is density of the liquid, which is 1000, into volume of solid is not given to us. We can find density is mass upon volume. So from where volume is mass by density. So mass of the block is given as 1 kg. The density in SI unit is 800 times the G effective is here. The G effective is G plus A, 10 plus 1. So this cancels out to be this, and 2 5s are, and 2 4s are, and we have 55 upon 4, which is 13.75. So now the weight is mass times the gravity, which is G effective again. So mass is 1 kg into G plus A, which is turning out to be 11 newtons. So if you find out the tension here by substituting the values of force of buoyancy and weight, which is 13.75 into 11, minus 11, which is turning out to be 2.75 Newton. That is the tension in the string. So guys, here comes a similar question for you to practice. Here the acceleration is now given as 2 meter per second square. A block of the mass of the block is 0.5 kg, and the density of the block is 0.7, and the density of the water and G value is 10. So you can find it out. Pause the video and do the problem. Okay, if you finish solving, you will get the answer of tension as 2.57 newtons. Okay. So, okay, in this video, we have seen 5 questions, and there are 5 similar questions for you to practice. You can pause the video in between and practice those questions and get the answer. And merely learning the theory does not work out for JEE Mains and Advanced. You need to practice some number of problems to get more idea into how the practical world works. Okay, so all the best for you, and practice more. Okay, and stay tuned. We will see you in the next video. I will be giving you further five problems each time with some practice problems as well. Okay. Bye-bye.